Which ESP32 boards can be used for our battery-operated projects? How can we distinguish between good and bad designs? And how do these boards compare to the ones tested in earlier videos? This time I have a global boards selection coming from Australia, Bulgaria, China and the USA. Grüezi YouTubers, here is the guy with a Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. Most battery-operated ESP32 boards use deep sleep to extend the battery life because the ESP32 chips only consume microamperes in this state. Unfortunately, this does not mean that the ESP32 boards also have a low power consumption during this phase. So, in this video we will present the contenders, create a setup to measure power consumption for the operating and the deep sleep phase. We will concentrate on the energy provided by the battery and not through the USB connector. We will learn that a big capacitor does not always prevent crashes. We will define the essential measurements to get long battery life as well as protect the battery. We will search for the design files of all boards and look into how they are made. Can we learn how to distinguish between good and bad boards for our future purchases by looking at their diagrams? With this information, we should be able to calculate the lifetime of a device with a charged battery. Now the contenders. The EzSBC IoT controller from the USA. The Adafruit Feather Huzzah. This is an older board also made in the USA. The ESP32 dev kit from Olimex, made in Bulgaria. The TinyPICO from the Unexpected Maker, made in Australia. The TTGO T18 board with built-in 18650 battery holder. The Feather S2, also from the Unexpected Maker. By the way, you can purchase all his boards also through other channels. The TTGO T8, also with an S2 chip. The TTGO T7 version 1.3 for comparison. It was tested in a past video, but is still my favorite board. First, we have a look at the design of such boards. All have the same components: a Li-ion battery, a charger for the battery, and a 3.3 volt regulator to run the ESP32 chip. Preferably, they also have a low voltage protection circuit to prevent a deep discharge of the battery, and a so-called power path, as discussed in video number 383, to directly feed the 3.3 volt regulator if 5 volts are available, and a way to let the chip measure battery voltage. Like that, it can inform you to charge the battery. The chargers are designed for 5 volt USB and have to comply with such a charging curve of a Li-ion battery. If it supports higher input voltages, we can connect a 6 volt solar panel directly to the board. Most boards only provide a connector for the battery, so you are free to choose the capacity for your application. Just a warning, plus and minus is not standardized on these connectors, so check before you connect the battery. The chance you destroy something is high if it is reversed. Because Li-ion batteries can be destroyed if discharged below 3 volts, we need a circuit that switches the load off in this situation. Otherwise, the battery can be discharged till it is entirely flat. The next component is the 3.3 volts regulator. Because a Li-ion battery can be charged up to 4.2 volts, we need a voltage regulator to protect the ESP chips, which only are specified up to 3.6 volts. Unfortunately, these voltage regulators have two undesired properties. First, they consume a bit of current for themselves. It is called the quiescent current. And second, they lose a minimum voltage between the in and the output, called dropout voltage. The regulators used on those boards are called low dropout or LDO regulators. Both values differ from part to part, and therefore it is crucial which part the manufacturer uses for its board. Next is a circuit to measure the battery voltage. As seen before, it can go up to 4.2 volts and the ADC input of an ESP32 only can measure 3.3 volts. This is why we need a voltage divider to drop the voltage. Keep in mind that these two resistors are across the battery and also consume current. The last point to discuss is the optional power path. It connects the USB or solar input directly to the regulator. It protects the battery from frequent charging cycles. If we talk about powering ESP8266s or ESP32s, we have to talk about current peaks and brownout crashes, and how to prevent them. Frequent viewers remember that I always recommended adding a beefy capacitor across VCC and ground of the ESP module to prevent crashes. Recently, I saw a video about this topic and decided to do some tests. Here is my setup. I soldered an HT7333 LDO on a breakout board and added these headers to insert different capacitors. Then I used this barebone ESP32 module on a breadboard. The setup is powered by the bench power supply set to 5 volts and an oscilloscope measures the voltage close to the ESP32 pins. When I went with the recommended setup from the datasheet, the voltage dropped considerably and a brownout was created. Then I replaced the capacitors with 100 microfarads and I still got these sharp voltage drops. But at least the ESP did no more crash. The input voltage of the regulator, by the way, only showed tiny drops. Then I added a beefy 1500 microfarad capacitor on the secondary side of the regulator and, of course, hoped that the drops disappear. Unfortunately, this was not the case. Using a more powerful HT7833 or an AMS 1117 regulator did not change the situation. Strange, very strange. Then I soldered the output pin of the HT7333 directly to the pin on the breakout board. This removed the resistance of the breadboard connections. The voltage drops disappeared and I learned that they were not induced by the regulator but by the resistance of the breadboard. So pay attention to your designs. Put the 3.3 volt regulator as close as possible to the pins of the ESPs. I also tried several capacitors and found that a 100 microfarad cap on the secondary side is sufficient to keep the voltage above 3 volts. No need for a bigger one. Of course, we will test the minimum operating voltage of our boards. This is important because it can reduce the usable battery capacity. Just out of curiosity, I tried several capacitor technologies. Tantalum and solid polymer caps were best. Standard electrolytic caps a little weaker. So I suggest using such solid polymer caps for this purpose. Let's start the testing. I will use the same setup as in my last video and replace the battery with a Power Profiler Kit 2 from Nordic to supply 3.7 volts to the battery connector. It measures and displays currents from microampere up to 1 ampere. Like that we will be able to compare the power consumption of the different boards. As in the last video, we will use a sketch with 2 phases. An active phase that connects to the internet and fetches some data, and a sleep phase. Like that, we can measure the current consumption for both phases. These 2 numbers can be inserted into a formula to predict the time a battery will last. Let's test our setup with the Olimex board. To avoid resistance, I soldered wires to the battery connectors. Like that, the resistance between the PPK2 and the board is minimal. I do 3 measurements. Deep sleep current at 3.7 volts. The minimum voltage, the board works without brownout crash. The current consumption at 2.5 volts. It should be close to 0 because we are in the danger zone to over-discharge our battery. All measurements are entered into the existing spreadsheet. What can we read from the numbers measured with the Olimex board? At a nominal battery voltage of 3.7 volts, the board consumes 72 microampere for deep sleep and 87 milliamperes during operation. My sketch runs around 14 seconds, which is quite long. If yours run shorter, your application of course also will need less energy. If we enter all these numbers, including the planned deep sleep time of 3600 seconds or 1 hour, we get a lifetime of our 3000 mAh battery of 305 days. Not bad. But if we reduce the sleep time to 10 minutes, the lifetime is only 37 days. If we could halve the code execution time, we would get 72 days. I think you get the point. Let's quickly check the diagram of the board. They use a rather typical BL4054 Li-ion charger and an SY8089 switching voltage regulator. And they implemented a power path. But as we saw, there is no proper minimum voltage protection. The regulator stops working at around 2.3 volts, but still consumes 37 microampere. And its absolute maximum voltage is 6 volts, so I would not directly connect it to a solar panel. And the Olimex board offers a possibility to measure battery voltage as well as the external voltage. Olimex did an excellent job in choosing the regulator and placing it close to the ESP32 pins. The board does not crash down to 2.7 volts. These are the tests we perform now with all other boards. The next is the EzSBC made in the USA. It has a simple setup. A A4056 Li-ion charger and an HT7333 regulator without a power path. As a specialty, it has a battery fuel gauge chip which, with the right software, measures and displays the state of the battery. The description says that it should have a deep sleep current of 12 microampere, which is very low for its components. My tests show 670 microampere. I do not understand why it is so high. The minimum voltage to run the board with Wi-Fi is 3.1 volts, as expected from a HT7333. It also has no undervoltage protection and the current draw at 2.5 volts is 38 milliampere. So the battery will be flat in a very short time if you do not use the gauge to monitor battery status and charge if needed. The next board is also made in the USA, the Adafruit Feather Huzzah. It uses an MCP 73831 Li-ion charger and an AP2112 LDO, including a power path. It consumes 7 mA or 7000 microampere during deep sleep, which is definitely nothing to write home about. The minimum battery voltage to run a sketch with Wi-Fi is 3.3 volts, and it has no undervoltage protection. At a battery voltage of 2.5 volts, it consumes 23 mA, which drains the battery quickly to below 2 volts if you do not recharge. Fortunately, it can measure the battery voltage. Overall, this is not a board for battery-operated projects using deep sleep. Because the maximum voltage of the charger chip is 7 volts, I also would pay attention to connecting a 6 volt solar panel. The next board is a true Aussie from the unexpected maker, the TinyPICO. I do not know exactly which version I have, so I assume it is the V2P2. Anyway, the start is not easy because it is delivered without the battery connector soldered to the board. Because it is an SMD version, 2 pads essential for stability are below the connector and not easy to solder with a soldering iron without damaging the connector. This is why I stopped my trials. The board is tiny compared with all other boards. It uses a TP4065 Li-ion charger, including a power path, and an NCP1678 LDO. This regulator delivers up to 700 mA. So let's check its performance. 505 microampere in deep sleep. Definitely not what I expected. Then I RTFM and discovered that I had to install a TinyPICO helper library to shut down the NeoPixel. Now the deep sleep current is 29 microampere, much closer to the 20 microampere specified. So far, this is the best value for all boards. The minimum operating battery voltage is 3 volts. Below that value, the board crashes. There is no low battery protection implemented, and at 2.5 volts, the device consumes 50 mA, which depletes the battery rapidly. Fortunately, it can measure the battery voltage. According to its measurements, the TTGO T18 is the best Chinese board. It consumes only 51 microampere in deep sleep and runs down to 3.1 volts. The 75 microampere consumption at 2.5 volts is okay to protect your battery for a while. It uses a TP5400 switching Li-ion charger and an SY8089 switching 3.3 volt regulator. In addition, it has an ME6211 LDO which is connected to USB. So it is quite different to all other boards, also because it has the battery holder on board. I would have also loved to test the S2 Feather battery operated board from the unexpected maker, but it did not upload via the Arduino IDE, and I did not find any documentation on how to program it with the ESP32 development release, also not on Adafruit's homepage. It exposed a serial port and presented itself as a disk drive called CircuitPy. So I assume I could program it in CircuitPython. So I tested the TTGO S2 board. It has a display and an SD card slot and uses a TP4054 charger and an AP2112 LDO. Interestingly, it runs down to 2.8 volt battery voltage. Its deep sleep current is 196 microampere, probably because of the display. It has no formal low voltage protection, but only consumes 280 microamperes at 2.5 volts, which is at least a little protection. And it has built-in battery voltage measurement. As the last step, I compare these new boards with my favorite because of its size, the TTGO Mini or T7 1.3 tested in an earlier video. It has no undervoltage protection and consumes 43 mA at 2.5 volts. The Li-ion charger is a TP4054 and the LDO is an ME6211. Its deep sleep current is 870 microampere if you desolder the LED, and it works only on a battery voltage of 3.5 volts. So no way to use the total capacity of a Li-ion battery. So this board definitely is not a good choice for battery operation. But it is okay for solar because you can connect a 6 volt solar panel directly to the 5 volt pins. All in all, we saw quite a few ESP32 boards with battery support appearing during the last time, also from different sources outside China. This is very good. Unfortunately, most boards are not well suited for an extended battery life because they consume too much power during deep sleep. And the lack of undervoltage protection is a pity. It only would need 2 cheap components. The Li-ion charger circuits are very similar. They differ mainly in the maximum input voltage. Many boards have a power path included. Also, most boards support the measuring of battery voltage, which is important because they kill your batteries fast if you do not charge early enough. For the 3.3 volt regulators, we see a wider choice. Most boards use linear regulators. Those boards cannot use the total battery capacity because they start to crash at voltages well above 3 volts. This is more dramatic than it sounds. If the ESP crashes, it can no more enter deep sleep mode and consumes a lot of current. So I strongly suggest measuring battery voltage and setting the ESP32 into deep sleep if its voltage is close to the minimum voltage. Like that, you can protect your battery. Flat Li-ion batteries often cannot be charged anymore. I included all boards and measurements in the existing table and extended the sheet with some new columns. I did not go back to the old boards to fill their values. You should know now how to do the measurements. As always, you find all the relevant links in the description. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. Thank you. Bye.